Hello, everybody, and welcome to today's Engineering Leaders webinar. The topic we will be digging into over the next 45 minutes or so is data, the importance of data, and particularly in the future of AI accelerated engineering. So my name is Alex Graham. I'll be your host for today's session. And joining me to take us through this topic are Steve Lanay, who leads application engineering and partnerships here at SimScale, and also John Wild, who is our VP of product. Now, before we jump into this, I'd just like to remind everybody we will have a live Q&A at the end of the session. You're also very welcome to drop your questions into the Q&A panel. There's a questions panel in your GoToWebinar window. Please drop your questions in there as we go along. We'll also be able to answer them possibly during the webinar. Also, we'll have time at the end to go over the interesting questions and answer any further ones that come up. So, without further ado, I'm going to hand over to John, who's going to get us started today.
Perfect.
Yep, you're ready to go, aren't you, John? Yep.
I'm ready to go. Thank you very much, Alex. I might make one correction as to what you said at the beginning, that we're going to talk about data. We're going to mainly talk about AI and how important data is for that, just to make it clear. It's quite an AI heavy topic, right? So we're going to cover four things. We're going to start with AI in engineering, why we're talking about it, why it's important, what are the challenges. Then we'll talk about the data challenge for physics AI, and then moving on to agentic AI, which we call engineering AI, and how that can be used more holistically than physics AI to accelerate larger workflows. And then why the choice of how you choose to build your AI, what technology you build it on, is going to be really important. We're going to break this up a couple of times too, so Steve will jump in with some pretty detailed demos, I think, one with physics AI and one with engineering AI. So it should be quite an interesting session. And Steve, feel free, if you want to interrupt and ask me any questions, then feel free to. Only easy ones. So the first thing we're hearing from our customers, I think is important, is the need for speed. I think this is totally true. And I'm going to share this across 4 different industries. So the first one in transportation. Our customers obviously in transportation get requests for quote or requests for proposals very often, and they used to have months to turn those around and get something back to the customer. Now that's come down to weeks, mainly because everyone needs things to be faster and there's competition that we need to be in front of. So there's a real need here to do things faster, but without growing the teams to do that. And we need to do it in a different type of way. Within electronics, our customers are releasing more products than they were a few years ago to maintain the growth that they had, that they need, that they must continue to have, but they can't build their teams in the same speed, so they need to somehow find more efficiency. Within industrial machinery, huge transformations are taking place, and our customers need to maintain their old product portfolios, still iterate on them and improve them whilst producing new ones and moving into new areas entirely. And then within medical devices, I actually say this to our kids: if you're not first, you're last. And I think it's kind of true actually in life often, that especially in business, if you're not first to market, everyone else is last. So the first one very often will win. And here we need to be first to market, and then we're already ahead of all of the competition. So everywhere we're seeing a need to be faster, but without at the cost of being efficient as a company. So if we kind of dig into what a process could look like in a company, the example I'll take is a request for proposal comes in, and an engineer or designer will start to produce a new concept, probably based on something they've done before, but they'll create some kind of design. Then there's some waiting period before the simulation engineer can do the simulation and figure out, is that a good design? Does it meet the requirements that we have in our RFQ? If not, that will go back to the designer. They'll produce another design. Hopefully this time it will work. there's again some kind of waiting time before the designer or before the simulation engineer can validate it. Hopefully everything's good, we get a tick in the box, and we can hopefully within time send our proposal back to our customer. And you can see there's a lot of kind of waiting time here, which we really need to do away with. And we've probably run 1, 2, maybe 3 iterations. So we've maybe improved our design a little bit, but we need to do better. But with this kind of structure, it's hard to compress it and it's hard to make things faster. So we need a different way. And I'd propose that way is giving the designer or the engineer early access to simulation and AI so that they can do these things by themselves, and we can really quickly accelerate the process. And this is what it would look like instead. So the quote, the request for a quote comes in, the designer makes their own concept and starts to do their own simulation so they can start to make things better and improve it themselves in the same day they've created the concept. They could maybe run 30, 40, 100 different designs, so they could start to explore a design space, find some candidates for the final proposal that could really make sense, hand those to the simulation engineer. They can decide, yes, this is good, this isn't, we've done better than we could have done before. This can be sent back and we can issue a proposal. So we've run through now multiple design iterations, hopefully with a much shorter time scale, and we produced a better design as a consequence, all by doing things earlier. So just by doing simulation earlier, we can have huge improvements. Then we could also layer AI on top. So this is where we'll start talking about physics AI and engineering AI. So physics AI sits in the middle. When the simulation part is happening, at the moment, how we looked at it at least, the designer is doing traditional simulation. So it's maybe taking an hour, maybe 2 or something like this to do every single iteration. Maybe they're running in the cloud so they can do it all in parallel, don't know. But if they've leveraged physics AI, they could have results within 2 to 3 seconds each time. So that within a few minutes, they've run 100 or 1,000 simulations. They've already got a design space and they've moved really, really fast. So physics AI speeds up this middle section. And then on top of that, we also have engineering AI. That could enable the designer to do even more without having to do the simulation themselves. So they could ask an agentic AI to start to do this work for them. We'll talk a bit about both. And Steve will also show both and how they work within SimScale a little bit later on. So firstly, a little bit more about physics AI, because that's the main topic of today, really, at least as to how it connects to data. So physics AI is instantaneous physics predictions, basically. So instead of running a traditional solve, we can get results really, really, really quickly. But we need lots of data. So at the beginning, if we're going to simulate a pump, we need to simulate lots of pumps, and we need to have a really well-described design space with lots of examples of high-quality results to train an AI model that we can give a new novel CAD model that it's never seen before and get then predictions in seconds. So we should then be able to leverage that model to get predictions on any new CAD model, as long as it's within the design space and pretty quickly. So the physics AI can use graph neural networks and physics-informed neural networks to accelerate that process. But the important thing to know is that it does need data. It needs pre-training upfront. Engineering AI is different. It doesn't really need that pre-training, and it can do different things. But first, we need to decide what we need it to do. So we need to find a problem to fix, and there's many. So we've talked to lots of customers, and we have an advisory council too that gave us some of these examples, and I'll share some. So one might be actually quite connected to physics. I need faster predictions for my standard use cases. But this means I don't want to set up my model anymore. I just want to have my CAD model, and I just want the results given straight back to me in the same way that I did last time. Or I have a parameterized model. I can explore that design space myself, but I want the AI to find things outside of that design space. Find something new that I wouldn't have thought of otherwise. Or this is a really interesting and really difficult one, but it would be amazing. Take a finished CAD model, so something that's production ready, not simulation ready, production ready, and get it simulation ready for me. So I don't want to have to go through the cleanup process, do it for me. Or I've got two more examples. One, I've run a simulation. I can see my results aren't great, and I want to talk to my AI agent in plain English and have it fix something. So I've got a high stress here. I wanted to go and update my CAD model, run it, and come back with a better example that I could then take forwards. Or at least tell me how, if this meets my design requirements. So I've got a request for proposal, got a solution. Have I solved it? Like, can you tell me? If not, can you make it better for me? And this works with giving engineers an agentic AI powered by a large language model, and together they can be really, really efficient. So they could do something like getting really automating a holistic workflow. So it could be something like getting a request into a request for a proposal, and then instead of having to go through all of those steps that we did before, going straight from the beginning to the end with the AI agent doing all of the heavy lifting and all of the optimization for us. We'll get into it a bit more later, but this is different, and it leverages engineering AI leverages large language models, and it doesn't need pre-training because they're already pre-trained. We can augment it with additional data to give it some relevant intelligence, but we don't need to pre-train it, which makes it really powerful. So taking a step back, over the last, I don't know when it was, Alex, 3 months ago or something, we surveyed 300 engineering leaders, and they helped us highlight or understand at least what's happening within AI, within the engineering industry. I thought I'd share 3 things. So one is the expectations are really high. So nearly all of engineering leaders expected something positive from AI, and 3% had achieved this, which is crazy. And I think it's because it's crazy small, by the way. I really would expect it to be much greater. I would expect much more benefit from AI. But I think it's because we're leaning quite heavily into physics AI, and it's hard because we need lots of data. Engineering AI maybe could be a different solution, where we don't need all of this pre-trained data and the blockers aren't quite so significant. So although adoption is in its infancy, there was a clear difference between between these leaders using traditional tools and those using more modern and cloud native tools. So you can see there was a 3 or 6 times more advantage for those who are already running in the cloud, because they've already got data centralized, clean, and easy to reference and to start using for AI. And the 2 largest barriers for AI adoption are kind of what I said already. One is siloed data. So 55% said that their data is all over the place and it's hard to use for AI, or their tools just aren't up to the job, which is also a problem. That one I can't help with directly unless you're using SimScale, obviously. But one thing I thought was interesting was the lack of in-house AI expertise, which 36% of people found this to be a problem. I kind of hate this because I don't think that when we enable engineers to use AI, we should necessarily need AI expertise in-house. It feels like we've solved one problem and we've created another one. We're not making people more efficient because now we need data experts as well. And it seems to be a bit unfair. And we're looking at it differently. I think we can solve it differently as the company. So I'll talk a bit about the data challenge for physics AI, and then also how I think we're doing it differently, not needing these experts. And then I'll hand over to Steve, and he'll give some examples too. So just as a reminder, this is what I shared before. So this is the instantaneous prediction of physics, knowing that we need lots of data upfront to be able to achieve an accurate result downstream. But as we know, and what we're probably all here, is that the data can be hard to come by. So it's often distributed across many sites, many computers, many users, all over the place, and it's really hard to put it together to use it. So like I said before, 55% of users find it really hard to pull data together for AI, which is a shame because there's really power there. I think, yes, using modern technology helps a lot, but also knowing that we don't need that many simulations to have something good. Something like 50 simulations can already give you a decent design space, so you can start to do AI predictions. So I'm not sure if we're as blocked as we think we are. But worst case, I think we should start collating data now. So start tagging everything you do, make sure everything's got metadata so that you can easily categorize it and then utilize it later. And PLM should be super useful for this, and SPDM as well. So I said just a second ago that 50 simulations is good. It's a good starting point for physics AI. Moving into the hundreds makes sense, obviously better. Once we're past 200, then we should have a really nice design space where we can start to do really trustworthy physics predictions. And also leveraging the cloud really makes sense. So simulation data generally is much bigger than all of the other data that we have. But if we can somehow keep it somewhere and then leverage it later, we're already in a much more advantageous position. So when you start to build up your data set ready for physics AI, I think there's 4 kind of tenets that are important. The first is relevance. The data must be relevant to the problem that you want to solve later. So yeah, it needs to be similar models, similar-ish kind of setup problems, all working within a pretty focused design space. So you're building up knowledge for the AI that's similar to what you plan to predict the next time. It needs to have good quality. So many of us have lots of different simulations run all over the place, but we need to know that they've been set up by someone who knows what they're doing, that it's been converged, and that we can trust the results. So if we give the AI bad results, it won't know that it's got bad results, and it will just use that data as part of the data set. So we have to be really sure upfront that the quality of the data we give it is really high. And we also want it to be diverse. So I just said we want it to be relevant and specific, but the broader we can make the design space, the more the AI can kind of experiment within this space as we start to give it and ask it to do novel things. And then we talked about quantity. So it needs enough data to be able to capture the patterns that occur within the different physics problems that we're giving it. So the main thing, I think, is that we should think about this kind of holistic design space. Probably it's in 3 dimensions. I keep doing a circle, but it's probably a sphere. And we need to make sure that we've got a really nice coverage of all of the different problems within this. Steve, you look like you're sinking, which is kind of interesting.
Sorry, just moving to standing.
It's all right. I might do it in a second when you're talking and see how that goes. So this is what the SimScale UI will look like. And we've done it in a way that is meant to be easy to use. And Steve will show you in a second. But you can bring in any of the different data that you simulated on SimScale really easily. So everything is available. You can choose what chunks to kind of pull together when you build your AI model. You could, if you wanted to, bring in third-party data to augment that SimScale data. I mean, lots of us have really high-quality data that we run in traditional tools for the last decades. We want to be able to use that and not disregard it. Then once you've created your model, you can visualize the data. You might have an outlier, and that outlier might be an outlier you want to cross out and get rid of, or it might be part of a design space that you want to augment because you need to bring that into the data set, and you can choose which way you want to do. Then once you've produced a model, you can share it with your team. Everyone can see who produced it. You can give documentation with it, so those users within SimScale who are leveraging it can see what it's meant to do. And then because it's working in the same way as the standard tools, the standard solvers within SimScale, you can run AI in a normal way, and then you can run a traditional simulation alongside it without any extra effort, so that once you've done all of this design exploration, you can validate it with a traditional solver that we all trust, just to make sure that you're happy with the final solution. Our customers are already doing this. So there's an example here where NAM2 are utilizing physics AI on SimScale. I think the important thing is, for me at least, that we've got thousands of customers and they're already building data ready for AI. So they haven't had to think about it, but we have. But they've got now thousands of, well, probably tens of thousands of simulations ready. So when they choose to start doing physics AI, it's going to be easy for them because they've already got the design spaces ready. They just need to choose what to bring in, train a model, and then they're ready to go. So they can already start doing evaluations really, really, really quickly. Okay, at this point, Steve, I'll hand over to you. I'll make you presenter. I think you did it by yourself.
Yep, perfect. Thanks, John.
Cool.
So yeah, what I want to do now is go through an example of how you can do exactly what NAM2 did and make use of some data that you've already built up in the organization to train an AI model and then make use of it for a new product development program. So in order to take you through this, I've got a video of the process. So we're going to start first by reviewing a data set that we already have in SimScale. So imagine that we're a company that produces hydraulic valves, and we've previously characterized a hydraulic valve in different operating conditions, different stroke positions, and different flow rates. So we can have a look at the pressure drop that we've analyzed over a sweep of flow rates per operating condition for this valve in the past. And we want to maximize the value that we're going to get out of this data. So this is the data set that we're going to use to train an AI model. So just having a look at the performance of this valve, we can have a quick check on the flow. And we can see that the ports that were used on this valve do constrict the flow quite considerably. We can see that using the flow lines here. We can see there's quite a constriction through that port. So in a future design, we may want to open these ports up if we want to use a higher flow rate, for example. So the second thing we're going to do here is actually create a new physics AI model using that data set. Now, this is incredibly easy to do in SimScale. All we do is go to the AI model management part and create a new model. Here I've used the name of that valve, HV0125, and then we select the data set that we want to use for the training. So I can see there's 82 simulations in there, and we can give it a version name and instruct SimScale what the outputs are that we want to get out of this model. So we're interested in the pressure. We say we want to train that as a global output. And then we select some other settings that we need. We can add cutting planes if we want to, but here we're just going to select to train the confidence score and then start training. So it really is as easy as that to create your first AI model. Now, rather than us sit here for 60 minutes and watch this, I've overlaid a stopwatch on here so that you can see how long it actually takes to train this model. It's trained on our GPU infrastructure in the cloud, and within 60 minutes, the model is trained. We automatically segregate some of that data for the regression analysis, and we can see that there's about a 4.4% error expected on the pressure from this model. That's acceptable for us right now, so we release that model and then we can make use of it. So in the third part here, we're going to see the actual use of this model. So you can see side by side. On the left-hand side, we can see a PDE solve of our original valve, and on the right-hand side, we can see the AI prediction. You can see we have a high confidence in the result, nearly 80%, which is good to see. And if we look at the pressure output, we can see our scalar prediction just under the confidence score there is a very similar pressure value to what we're seeing from the PDE solve. So it's a good first model. So we've created that model based on the original valve that we had designed. Now we have a new product design that we want to create. And as I mentioned, we noticed some restriction in the previous valve. And we want to push this to a higher operating flow rate. So the designer may choose to expand those port sizes up to a higher value. And we have a parameterized model here in Onshape that we can use just to set up the simulation for the new product design. So we can change the stroke length to look at all of the different operating conditions of this valve and change any of the parameters. So it's quite a simple design change in this circumstance. We've just increased all of those ports to get a higher flow rate through. So let's see how that first AI model performs, that physics AI model that we produced based on HV0125. So we can start a new project in SimScale to analyze this new design. And this could obviously be a design engineer that's done a quick change to that original valve body in response to an RFP from a customer asking for a higher flow rate hydraulic valve. So they bring in that CAD geometry from the CAD tool and then use the original simulation as a template for this project. So they bring in the previous one and then just literally swap out the CAD to the new 7mm port design. So thanks to the associativity in SimScale, all of the boundary conditions, material assignments are maintained. And all they have to do is bring that new CAD in and then run the AI prediction to see how it would perform. So the first thing we'll do here is run an analysis at one of the flow rates that we used previously for the old design. So we're using the midpoint flow rate and having a look at how that would perform with the AI model that we have just trained and shown the accuracy on. So with this completely new CAD, we get 80% confidence on the pressure results within an operating parameter space that was used previously. So it's quite nice that we can predict on a new CAD geometry, but as we mentioned, we would want this design to operate at a much higher flow rate. That's why we're changing the design. So now you can see we have a 0% confidence because the AI model is now extrapolating outside of the data that it has for flow rates. So in order to expand the data set, we would need to create some more simulation data. So we're using a new sweep of flow rates, 40 flow rates that go up to a higher flow. And then we can start a new parameter sweep in SimScale that covers this new parameter space. So exactly what we would do if we had to characterize a new valve anyway. But the great part of this is we can then use the data that we get out of this new study to improve our AI model so that we can then use it for future designs and future RFPs. So in this stage now, we're going to retrain the model. We can see the results here of the CFD. The larger port sizes are really helping to carry a higher flow volume. So let's use that simulation data now to improve our AI model. So we go back to that HV0125 model that we had trained, and then we create a new version of it. And all we need to do for the new version is select the additional data sets that we want to include on that model. So this will now have 164 runs in it. We give it a new name, and just like we did before, define what we want to get out of the AI model. So the pressure results, we may choose at this point that actually a cut plane is good to include, so we can include any of the new complexities like that into the new version of the AI model that we're going to release. So yeah, we're adding the confidence score and then just setting this off again. And just like before, rather than waiting for this to complete, I've overlaid a stopwatch on here so we can see how long it will take. So we can see it's running. This obviously doesn't affect the model that we've already published out to the design community. We can create as many new versions and keep them unpublished. So there it took just over an hour. We can see the results again of the training loss, of the automatically segregated unseen data that's tested on each epoch of the training to see how the new model performs. So if we're satisfied here, we can then release that again to the community, and this will replace the HV0125 model that we published out previously. So now we've got a new model. It's immediately accessible to everybody that needs to use it. So let's have a look at how that actually performs. So back in SimScale, in this same project, let's have a look how the new physics AI model will perform for our new design. So we have the larger 7mm port design, and let's analyze it at the higher flow rate. So remember, previously, this showed a 0% confidence score, and the pressure field results that we saw in the viewer didn't look accurate either. But now we get a 93% confidence score just by adding a few more simulations. We can see the pressure results look reasonable as well. So we would be able to use this on the next RFP that we get into the organization for a higher flow rate valve design. So let's have a look at that side by side as well as we did previously with the PDE solve on the left-hand side and the AI prediction on the right-hand side. Just adding an inspect point, we can see the pressure on the PDE solve is very similar to the pressure drop that we predict using the AI solve on the right-hand side as well. So you can really see, using this simple use case, now an existing data set can provide you a lot of value by creating physics AI models from it. But those physics AI models aren't static. As you create more data in your organization, you can constantly grow and retrain the models so that they're always improving. The more simulation data you have, the better the physics AI models are at predicting what the results are likely to be. All right, thanks. I'll hand back over to John for the next part.
Nice one. Thank you very much, Steve. That was interesting, really cool. I'll now cover agentic AI, which is what we're calling engineering AI. So this sits above, as I see it, physics AI, and it can automate lots of interesting and difficult workflows for us. So if you remember, this is the slide we had before, where we've got some examples of things that we could do better, that would bring huge value to our company if we could automate any of these different things. So pairing an engineer with an AI agent. And an example of one of those things working, I'll show in a second, but this is what we have inside SimScale. So this is where we can train our own AI agent. So like I said before, we don't need to pre-train this because we're using a large language model. We already have all of the intelligence that comes with that model. And all we need to do is augment that data. So I've written it on the left, but you can also see it on the right. We want to give things like custom prompts to say, okay, you know, if this happens, do this. If you get asked to calculate a CV value, here's how. Or we could give it some useful documents. We could give it the request for quote document that we have. We could share some reference simulations that we've done before. So you can start to give it relevant intelligence so that next time you ask it a question, it will know the right direction to go, and you can build an agent to really, really help you with specific tasks. Steve will also show this in a second, but I think it's worth showing what we have and that you can start to build all of this interesting customization. So the main takeaway for me is that this is different to physics AI because it doesn't need pre-trained data. It doesn't need you to bring pre-trained data. It is already trained because we're using a large language model from one of the large suppliers that are out there already, but we can augment it to make it really valuable for our specific use cases. An example of this is here. So a request for quote comes in from a favorite engineering company that goes, because it's our favorite company, goes to our favorite engineer, and they work with our SimScale AI agent collaboratively to run through this process. So they'll say, okay, I've got my new RFQ. You've already got the RFQs we've had before, the results we've had before, you've seen the CAD models that we've produced before, and the simulations. So please just give me a proposal to send back to the company now. And the AI can do that. So it can take the inputs from the PDF and it can understand the outputs because we've given it reports that we already have. It can take the CAD models that we have and iterate on those to make the right CAD models for the right problem, and it can simulate them on SimScale. If we need it to, it can optimize them so it can go through a loop until it finds a design that meets the requirements. Then, because we've given it a report, it can produce another report that's very similar with updated results ready to send back to our customer. And if we want to, we can leverage physics AI on top of that to speed up that optimization loop. So that's why I see engineering AI as kind of above, because physics AI is kind of a microcosm of that, and it can really speed up the optimization if we want it to. Now, again, I'll hand back to Steve, who'll show you this in action. But you're muted, Steve.
Okay, perfect. Thanks, John. I know we're starting to run out of time a bit here, so I'm just going to do this super quickly just to show what's possible with engineering AI. So if I go to my SimScale dashboard, I can then access any of my projects, and I'm going to use one of those hydraulic valve projects that I showed you previously. So if I have this project and I want to use the SimScale AI agent here, I can use it to help me. So, I could ask, what is this simulation as an example? And it has full access to SimScale. It has full access to a large language model. As John was saying, it's able to infer exactly what is happening here. So it could really help you pick up from where somebody else has left off on a simulation job and understand what's happening. Now, if I need to understand something like the CV performance of this valve for a new RFP that we've received, I can also ask high-level questions like that. So I could say, can you calculate the CV value for this valve? So then it's able to actually infer what it should do in order to calculate a CV value. So it's able to make us some recommendations here about how it would be done. And it asks if we want to go ahead. So yes, go ahead. And it's going to run the simulations for us so that we can make the CV value calculation for this specific valve setup. So that's a really quick introduction to what's possible with this specialist agent that we have running in SimScale. Obviously, the power of this is you could have many of these agents being orchestrated from an agent orchestration platform to be able to run much more complex scenarios. There's a short video here that shows the agent running outside of SimScale, just to show how this can be entirely possible to have an agentic workflow that isn't run directly in the web UI as we just saw it. It can run as part of a much broader workflow and can be plugged into many different systems. Okay, so combining physics AI and engineering AI is one of the areas that can be really powerful. And I saw a question come in about what would happen if we didn't have associativity when we swapped out the CAD geometry to do a physics AI prediction. Well, this is one of the situations where the two systems working together can be really powerful. Because in that scenario, you could have a workflow where the engineering AI actually sets up the new simulation based on past simulations that have been done, and physics AI is used to predict the results. So you remove the error possibility of losing that associativity or making wrong assignments. So in a traditional simulation process where you have a design intent, the designer will create new designs, they'll be passed over to the simulation team, and you have time to do some iterations and create a result. But in SimScale, we have a vision that this isn't going to be how engineers are going to work in the near future. They're not going to be sat assigning boundary conditions, assigning materials, handing off projects between each other. They're going to own the design intent. And they're going to work with engineering AI to automate all of those manual steps. And they'll communicate with engineering AI through natural language processes such as Slack or Teams or email. And they'll work with them as though they're an employee. They'll leverage things like physics AI in the background and other specialist agents to drive CAD geometries, run optimization studies, and really do things like optimization study that can happen in real time, exactly as you're seeing it on the slide here. So the CAD has changed. Instead of running a full PDE solve, there's a physics AI prediction run on it. Based on those results, the agentic AI decides what CAD to generate next and really hones in on a parameter space of interest that is optimized. And then you can explore that in much more detail with PDE solve technology or physical testing. So in order to achieve all of this, your choice of tool stack is pretty critical. With SimScale, we empower engineers to innovate faster by exploring thousands of engineering decisions in seconds. We have the platform to enable organizations to leverage physics and engineering AI. How do we do that? Well, SimScale is completely cloud native. We have integrated data management so that, as John said, without even meaning to, just by using SimScale, you're already preparing for the AI revolution. You can collaborate very easily on the platform because it's cloud-based. We have physics AI built in to be able to do instantaneous predictions, and we have engineering AI to support much larger agentic workflows, or even do very simple things like translating a simulation into your natural geographical language. We have broad physics capabilities, and SimScale is entirely scalable. Now, a lot of this is thanks to the platform that we've built up, and we've made it possible to be able to leverage AI. So for data and computing, we take care of all of the HPC provision and the data management. Everything you see in blue is what we can do today, and in gray is what's coming soon on our roadmap. So ingestion pipelines to be able to use training data from third-party solvers, deployment flexibility to be able to deploy on other cloud platforms. We have multiple physics, and we're also integrating third-party solvers to be able to bring in alternative data sources and also be able to solve on traditional solvers on the SimScale platform as well. We have full orchestration to be able to run engineering AI, user management, administer the whole system. And we will, of course, enable the ability to be able to use third-party agentic AI platforms as well. So you can have full AI agent workflows as well as the traditional simulation capabilities all on one intuitive platform. So we don't have much time to cover this in detail, but the traditional incumbent tools don't provide the integrated tool stack that you need to be able to support the AI revolution. The data is too segregated. It's difficult to deploy models once you have trained them. There's little or no management of those models once they're deployed, and not everybody has access to AI and PDE capabilities in the same tool set. With SimScale, we take care of all of these concerns. The data is well managed, it's automatically prepared. You can train the models extremely easily, and you can manage the deployment of them. So, how will you leverage AI in your workflows? However you are going to do it, we're ready to support you. And the next step is we would encourage you to identify engineering processes that you would like to do faster, that you think could be improved. What would be valuable for you to collapse the lead time from days or weeks down to seconds? Some of those examples are running stress analysis or frequency analysis or thermal analysis in seconds using physics AI, generating different design concepts and finding optimal designs, and really compressing the RFP response time, making use of data that you've already built up. And John, was there anything you wanted to add at this point?
No, I don't think so. Thanks, Steve. I think that's really interesting. We just look forward to further collaborations in future as people bring their ideas that we can solve with physics and engineering AI.
Perfect.
Lovely. Thank you very much to you both, John and Steve. Very good timing as well. Gives us a few minutes to just address a few questions at the end. So we had a few come in, particularly during your lovely end-to-end demo there of the whole physics AI training and even retraining process. I see some of them have been answered already, but I think it could also be helpful just to kind of mention a couple of them. So I guess not everyone's probably been following the questions panel. But yeah, one that we don't currently have an answer entered for is, it's a good one. How does the AI model estimate the confidence? So we saw that confidence score on the screen, but how does that work?
Yeah, it's a really good question. So the AI confidence score is a measure of how much the physics AI model is interpolating from the data that it had available in the training data set and how much it's extrapolating outside of that. So when we had a new CAD geometry that had diameters that weren't seen in the training data set, the confidence dropped from 80-something to 70-something, signifying that we had a slight change, but we still had confidence in those results to a reasonably high degree. But then when we also changed the parameter space to a flow rate that was outside of what had been seen during the training data set, the amount of extrapolation went beyond what would be useful. And that's when we got a 0% confidence score, and we could see the results weren't physical in the graphical representation of the pressure results as well.
Lovely, thanks. We had another good one, which was about the model ownership. Like if you train a model in SimScale, which is based on simulations which are using proprietary methods, like who owns that model?
That model would entirely be owned by you, by your organization. You author that data, you train that model, and you own it. It's hosted on the SimScale platform, but just like any other data that you put on there, it's entirely your intellectual property and your data.
Maybe I'd add one thing there as well, Steve, because I don't know if all companies do this, at least the LLM companies don't. But we'll never use any customer data to do any training on ourselves either. So your data will always remain your data, and we have to fix that problem by ourselves and make our own data if we want to do our own training.
Yeah, it's a really good point.
Thanks. Just had another one come in. Is there a template are there template choices for a model? Can you add features to train for templates? I'm not sure if I've understood the question correctly, actually. But I think, I mean, templating. Say again, John?
I'm trying to understand it too. I think so there's two things. We have templates inside SimScale that you can use as a simulation. So you can import a template and that will give you a simulation. So you could use that to run lots of simulations to build data to train for a model. But I don't think we necessarily have a template for an AI model, normally because it's so specific based on the data you want to bring into it. But it's really easy to do, so I don't know if we necessarily need one. Does that answer your question, though? Let us know at least if it doesn't.
And then we had some about context, I guess, yeah, and in the context of the LLM, so the agentic AI that we saw demonstrated, how difficult is it to provide the context that the agent needs to, understand and make decisions, and is that context very specific for each model?
Yeah, so what we saw here and what John stressed is the engineering AI, it really doesn't require much training. So what we saw here is a completely vanilla engineering AI agent. It's a specialist agent that's able to run simulations, but it doesn't have any additional context about me, my role, etc. So this can only get better than what you saw today when you're actually adding training data on your organization. So you can add a lot of extra information in the context window at the top that wouldn't be seen by the end user, but that can describe who I am as the user, what my role is, what I normally simulate, what my role is in the company, who I work with, etc. And it can also include lots of standard operating procedures, etc., that you have built up in your organization that you should be following when you're running these simulations. So it can follow those as though it is a veteran in your organization and knows how to follow all of those procedures.
I'd maybe add, because there's a couple of other questions coming too, and I can probably just add to the end of that, that you can create multiple agents for multiple scenarios. So you could have, for example, a pump agent, a valve agent. So yes, it can be quite specific. The context can be specific, but it's okay because you can make a use case for, you can make an agent for that use case. And someone else asked, can we train our own LLM? So I guess it must cost OpenAI and the others billions now to train LLMs. So we're not training a model exactly, but we can customize it. So it's just like when we use ChatGPT or anything, we can't train it, but we can give it custom prompts and we can give it our own information so that it can make the right decisions based on what we need. So we can really fully customize it ourselves. You can make your own agent for your own uses, but we can't create our own models from scratch.
And yeah, a couple more just came in. One about availability. Is this an add-on that we're describing, or is it already included in any plans?
Yeah, so this would be an add-on to your SimScale setup. And if you're interested, please reach out and we'll have a workshop with you. We're busy all of the time with our existing and potential customers running AI workshops now to understand where exactly we can add value to the process and how engineering and physics AI can be enabled for you.
Lovely. Yeah, well, maybe that's a good one to end on. So yeah, please get in touch with us if you'd like to learn more, if you're ready to start the journey. I think we're out of time for today. Thank you very much, everybody, for joining, for all your interesting questions. If any come in, or if you find that we haven't answered any fully, we will of course follow up with you directly. And you should also get a copy of the recording and the slides in your inbox in the next few days. So that's all from us. Goodbye for now. See you next time.
Thanks all.
Bye.
Bye.